Thank you very much. Thank you for inviting to this Marine Technologies workshop. And my name is Uldis Bethers. I'm director of the Institute of Numerical Modeling in the University of Latvia. My background is physics, but mostly our group is doing numerical modeling of almost everything. But one of things is oceanography, and particularly operational oceanography. And if you do some marine modeling, then from this you can develop some products. And one of such technologies which addresses coastal zone of Latvia and port areas, including port aquatories, is an information system HywasPort. I will show what is it, what's behind it, and what's new in it. This system is developed by the help of Copernicus Marine Service. There is user engagement projects running occasionally. The main thing is that Europe has quite good Copernicus services, both atmosphere service, marine service, and other services. But the results are quite complicated and require some special skills. In our case, we use them as boundary conditions. Okay, so the idea of this HywasPort product or service is quite simple. By the nesting of models, we can blend together what's happening in the sea with what's happening inland. For instance, in river estuaries, in port aquatories, and so on, you see these small places. For instance, here Riga harbor, where we have marine model outside and some riverine model inside. And also in the modeling community, sometimes these two people don't speak to each other. Groups of people, of course, or groups of researchers. People who are doing ocean never do rivers or lakes or estuaries or whatever. Anyway, if we go for the summary of this system, then recently by my time scale means few years ago, in 2024, 2025, we developed two new downstream services in our HywasPort system, well, of course in Baltic Sea, in Latvian waters. We developed this blending or seamless transition between the sea and inland waters. And second thing, we did something for the sediment transport in coastal zone. And in this system, we also have some observations by port authorities and third parties, for instance, Latvian Environmental, Geological and Meteorological Center. And here is the link, probably, if you wish. But you can access it through WaterLV. It's quite easy to find. Okay, let's see what technologies are behind the scene of this online system. We take two Copernicus Marine Service products, which are called Baltic Physics and Baltic Waves. These are operational forecast products, and we took just boundary conditions from them. So the outer points and time series, of course. When we run hydrodynamics in our modeling domain, it's a Hiram Boost model in operational setup by University of Latvia. So it's run on our premises on, we can call it supercomputer or computing cluster of my institute. And we are also a member of Hiram Boost modeling consortia, and hopefully this Hiram Boost model probably will be open source. It's in transition at the moment. Whatever is the model itself, the main problem always is to implement, set up, and customize the model. We have did it for parts of Baltic Sea, except Bothnian Sea, Gulf of Bothnia, and that's it. Sea and some Danish waters, but Botnian Sea, we have 7 levels of nesting in our model. Yeah, that's it. Sea and some Danish waters, but from nautical mile in far sea down to tens of meters for inner ports where berthing places and maybe some shore areas is very important. Then for waves, we use in-house model for port aquatories and do not calculate waves outside, just use a Copernicus product. And these days we are developing artificial intelligence or better neural operator model for operational calculation of wave field because strange as it can be, modeling of wave fields nowadays is more computationally expensive as computation of hydrodynamics, mostly because of very fine meshes which are needed for discretization of computational domains. Yeah, okay, and for sediments, we use HywasPort model, where are appropriate models for the sea in our setup. And inshore, in-house sediment transport models for the coastal area where we calculate longshore sediment transport in wave breaking zone. Of course, setup of HywasPort model doesn't allow to account for wave breaking, which is sometimes happening in depths of tens of centimeters. So it's about models behind it, and now let's go for the services. One thing is seamless transition between the sea and the inner ports. As you see in photograph, the sea weather can be quite different behind the wave breakers. You see this wavy conditions outside and quite calm sea inside. And if you go for navigation, when captains of ships encounter a rough change of sea state at the sea gates of the harbors. And this is a part where most of the traditional models fail to provide a good solution because you model either the sea and put the boundary conditions at the sea gates, or you are modeling the river or estuary or port aquatoria, whatever, and put your boundary conditions in again at the same sea gates. And so we try to use this nesting, which is available in HywasPort model to overcome this problem. And in our model, when this transition between the open seas and the inner port is quite seamless. For waves, currents, sea level, sea temperature, salinity, and wind is not in our model, but it's very important for the navigational purposes and other port operation purposes. And if there are some observations, of course, it can be meteorological stations or wave rider buoys, as it in Liepāja Harbor, and I think also in Skulte Harbor, then they also can be included. So let's see how it looks like. For instance, I will show some examples on Liepāja Harbor. Liepāja Harbor is quite interesting because it has 3 gates: Northern Gate, Main Navigation Gate, and Central Gate. Here you see the wave field by the color scheme. You see how the waves go inside the aquatoria, and you see that there is no disruption, and more or less it's smoothly these models represent the wave field. Despite that outside we have Copernicus product and inside our in-house wave model. And you also see that wave field in the harbor may be quite unpredictable if you just go by common sense without modeling. And it's quite good to have 2 days ahead forecast for planning your berthing operation or some movement of your vessels inside the harbor aquatoria. If it's a port like Liepāja, where huge territories are exposed to waves, you see what they have built internal wave breakers and jetties just to protect berthing areas from seawaves. Yeah, and here, of course, you have northern winds, and it's not the most dangerous situation. So let's go further. Here is example of salinity and currents. It's also somehow quite interesting because in so-called commercial channel, there is connection between the sea and Liepāja lake, which is also modeled as a reservoir, is quite good, but it's shallow lake. But we model hydrodynamics also there in MarTe River. You see the plume of brackish freshwater coming out of the lake in this situation. There are some westerly wind situations when seawater can intrude also in the lake, but it's not the case in this modeling scenario. You see also that here is some transit flow in probably the water is entering the northern gates and flowing out through central gate and this one. By the points here are shown some specific points of interest or observation stations where some data can be also shown as graphs. Let's go further. Here is an example of a graph at the main navigation gate. At this station, Liepāja Harbor has installed a wave rider buoy, and you see by dots in this graph the wave height, measured wave height and wave direction, and by continuous line you see the model results, which also somehow helps for validation if you go to study this for some scientific reasons. Yeah, and model performs quite well, but I think it's not a story I'm going to tell you today. The next graph is some example of water level. Water level is also important, especially for smaller ports where low water levels may limit the passage of the ships in the sea entrance channel, and also loading of the ship, how much you can load in it, if it's because at lower water levels you operate in more shallow conditions. And here again are two water gauges. This is in the lake. As you see, the lake experience quite smooth and stable water levels with slow change. And then there is fluctuating seawater level, which is lower in this case. As you see also here, the water is mostly flowing out of the lake. But here, previous to current time, there have been some time moments when water is flown in opposite direction. Therefore, you see salinity, which is non-zero in the navigation channel. Yeah, and the solid line is hindcast and prediction of the water level by the mathematical model, operational mathematical model. So now let's go to the second service, which is new in this HywasPort system. We are the nice words is supporting of coastal management and marine conservation in Latvia. And the things we are showing in the system are also listed as seabed disturbance indicators in the coastal zone if you go for a different classification of processes. But actually, we do two things. We included the operational map of sediment flux density just to see where and how is potential sediment flux in the Baltic Sea. And another thing, we put some mesh of points along the coast of Latvia for calculation of longshore sediment transport in multiple locations. Yeah, and then we can see how this longshore sediment transport can be compared with climatic values like seasonal and annual cumulative values. How this season compares to the 20 or 30-year long climate of sediment transport. Okay, I will show you how it looks. Again, we have plenty of these points or regions. There are some pictograms on the screen. For instance, we can take Ventspils Harbor. It's somewhere. And when we have this sediment, longshore sediment transport cross sections, which are also somehow named. And on one of the fields which can be shown in the open sea is the density of the sediment flux with some units which seems strange, but is the only meaningful units if we go for sediment transport. And of course, more sediment transport is closer to the coast. There is a wave action, the typical mechanism how the sediments are moved in the open seas, but waves mobilize the sediments and then the currents carry the mobilized sediments away somewhere. Yeah. Typically in longshore direction because the currents cannot cross the sea land interface, and so they are always parallel to the coast. If we go for cross-shore sediment transport, for instance, taking this profile, it's a vertical. I'm sorry, it's cross-shore profile which is perpendicular to the coastline, and we calculate the longshore sediment transport. The longshore sediment transport is the feature which dominates the sandy coasts, and Latvia has sandy coasts, of course. And this sort of phenomena occur because part of the wave energy, especially in wave breaking zone where this energy dissipates the most, is transported to the so-called longshore current. So this wave energy does two things. Breaking waves create suspension of sand, and part of this wave energy transforms to the current. It's a dangerous sort of currents which carry away swimmers as well. And this current carry away along the coast also the sediment. Yeah, and for each of these cross-shore points, in our case, we took sediment load at Majuri, we draw 4 lines. We have pre-calculated the climatic sediment transport in eastwards direction and in northwards direction. You see that most of the sediment is carried in towards Riga at this Majori point. And when we calculate the sediment load which happened during the last year. I prepared this screenshot in April, May 2025, and in that time we can see that this sediment transport in eastward direction was smaller than sediment, or of the same magnitude as sediment transport in westward direction. And we also could see that the total sediment transport was smaller as a climatic value. And if you remember last year when there was a quite strong storm in 30 of, I think it was 30 of July 2024, when there was a big damage in Jurmala, where also the farmers complained about loss of crops in Zemgale region, and it was heavy thunderstorms, rain and northern wind. This profile was exposed to this northern wind blow in this direction, so the sediment moves to westward, and it's this very big event. And one can see that all events of sediment transport, most of the sediment transport occurs in the event, like here, and so on. Yeah, okay, let's go further. It's the same for in the seasonal. Time scale and season in this case is 3 months from the current day, and there again in April 2024 there was a small storm which can be shown here. And yeah, one can see how we are doing in the climatic context in different places. Of course, for ports, it's also important because there is possible to relate this information with siltation in the sea entrance channel, which is one of big issues also in your port city. So what else? Yeah, thank you for attention. I think I also saved some time for questions. You can access the system at this address, water.lv HywasPort, or you can go for water.lv to see some other free products by our institute. I don't know why people advertise free products, but I'm doing it at this moment. And if you want to learn what we are doing, you can visit our webpage or write me an email. And I also, well, last but not least, I also invite you to one conference in Riga, August this year, Artificial Intelligence for Inland Water, Atmosphere and Ocean, if you are interested. So that's it. Thank you.
Thanks a lot. Thank you for your talk. It was very interesting and interesting products that you are delivering. And I understand this is already online, water.lv, everyone can use it, right?
Yeah, it's online, and I will stop sharing. This system is online, I think, for some 5 or 6 years. We have also some user community. It is free, and it is free mainly because our main profit is from developing to put in place some subscription system where you get 5, 10, 20, or 2,000 euro per user, it's not easy. And it is also harmful for your public relations.
Sure. So yeah, but thanks a lot. So it's interesting. I have a couple questions. Maybe if any from audience on no online, and so also no hands. But about prediction. So this system can predict up to 2 days, as I understand correctly.
More precisely, for 54 hours, but it depends.
But it's also counts some kind of extreme events like storms or snow melting and floods, or it's not included, or it's not possible in this
Yeah,
case.
everything of it is included, but in the in the system there are parameters which are listed. There are marine parameters mainly, and from atmosphere parameters there are just two. It's wind speed and direction and air temperature. And if we talk about sea ice, I think it's oceanographic parameter. There is quite sophisticated data flows. We use numerical weather forecasts plus Copernicus boundary conditions and Copernicus wave field in open sea, and then we run our models. And of course, with operational weather forecasts, operational Copernicus products, and operational wave fields have this future component of, say, 60 hours.
And for inland waters, it's the same models or it's something different?
Yeah, it's we run a nested Hiram boost model.
Yeah, thank you.
Okay, what I'm showing, everything comes out from our models. We use this atmosphere and Copernicus far sea points as a forcing. So it means 4 times a day in our computational center, we rerun these models for the next 54 hours. So it's routine task, which is maybe not that typical for university. But this system, once it's set up, it runs. You need not to put much effort.
And covering it's cover Baltic Sea or just Latvia, Estonia?
The model, the model area covers most of the Baltic Sea, but the visualization area, which is or this front page you see, covers a limited part of Latvian coastal area and limited number of ports. And we have 8 ports included in our system. And only for 3 largest ports, we have also hydrodynamic model inside. It's for Liepāja. Obviously, you saw it, yeah? For Ventspils and for Riga. In our hydrodynamic models, we run also Liepāja Lake, Ķīšezers Lake, Jugla Lake in Riga, and also Daugava, starting from Riga hydropower plant, and Lielupe River starting at upstream point near highway to Ventspils Bridge. But these parts are not included in visualization because it requires some effort in data transfer.
Thank you. Maybe one more curious question about sand and seabed movements. Is it constant? So in your plots, it's like a average per year, some cubic meters. I just worrying about wind spills. So is it all times same direction and like a sand moving?
No. At
Right.
every moment, it's in different direction, but most of sediment movement occurs during strong events. Uh, it's if you are looking for operational things. If you are looking climatically, then of course these lines become smooth. Because in climatic means every winter day there is chance of a storm.
Mm-hmm. Yeah. Thanks a lot. And so if no questions, so thank you again.